Hey, all right. So welcome everybody. We're a couple minutes late getting started due to technical difficulties. We may need somebody to kill the lights a little bit depending on how you're able to see the screen here. So welcome. I think that's okay, unless somebody needs light a little bit later on, we'll put the back light on.
Just let us know.
All right, so welcome to our June meeting here. The agenda this evening, we have the welcome and introductions, book of the month, some events and outreach notes. Our main feature presentation, our talk from Dr. Vanderlei this evening. The SeeStar transfer has actually already happened, so that'll be very quick. Wayne gave us a little what's up in space item to go over, shallow skies. And we got a ton of member astrophotos. And as usual, some of them are just absolutely spectacular. So that'll be fun to go through. So that's what we will be doing this evening. So the first thing we usually like to do is to start off and see if there's anybody new to HAL that is here, somebody who's not been here before. Would you like to raise your hand and introduce yourself?
My name is Bob Buchanan.
Bob Buchanan. Hi, Bob. Welcome. And how did you just join recently, or?
I just joined the end of May, just recently retired and have received a telescope as the present.
Wonderful.
And so wanted to have an opportunity to learn how to use it and to use it.
That's great to hear. Do you know anything about the telescope, the size or anything?
I did when I.
No worries. No worries. Didn't mean to throw the white hot spotlight on you there, but that's fine. And welcome.
4S.
A what?
4S.
Okay.
Yeah.
Awesome. Very good. So anyone else? Or yes.
Lucas Martins. I'm just his son.
Okay. And Dr. Vanderlei is here.
Vanderlei Marks. I'm just his dad.
A little circular logic there. Okay. Anyone else in the room here that's new to HAL? Okay. Anybody online? Okay. Well, absolutely welcome. We're always happy to have new members. Dave, you're up.
Evening, folks. A little bit of a different swing this month in terms of books. Actually, my copy is probably a little bit older version of What's Out by E.C. Krupp about ancient skies, lost civilizations. It's always very interesting just to kind of look and see if whatever knowledge you have, or maybe you might want to learn about how other ancient civilizations looked at the night skies and what they use in terms of whether it was everyday life or religious practices, whatever it might have been. But this book does really a nice job of covering that. And I just came back from a couple of weeks in Malta and Sicily, and some fascinating looks at some of the Greek temples in southern Sicily. In fact, one of them is even better preserved than the Parthenon and the Acropolis in Athens. So it's really interesting. So it's also kind of sparked my interest in this. If anyone has interest in looking at this, obviously it's not something that is thin, but it is well illustrated and fairly easy to understand and follow. So that also double check, make sure I wasn't in the library. So
Dave, is that in the HAL library, or that's just your? It's not. Okay, yeah, so you would need to purchase that.
Yes, so I'm going to add it to the library. So yeah.
All right. Any questions? All right. Thank you, Dave. So we had a lot of HAL impromptu star parties over the last 30 days. Kind of like summarizing what I saw come across, which is I really appreciate when folks kind of like make that little star party report and they give us details about what's going on, who was there, what they were looking at. That's really kind of cool to see what people are doing and kind of motivates people, I think. So basically there has been consistent turnout and very good engagement. Each event drew about 5 to 7 members, with a mix of people who were imaging and people doing visual. It's kind of cool to see people still doing visual. I know we get a lot into the imaging, but there's still a lot to be done and enjoyed, behind the eyepiece. Strong imaging activity. Members captured classic galaxy season. The spring, of course, is one of two galaxy seasons. M51, M101, M104, Mark Heron's chain. And later, as things progress, the nebulae and globular clusters. We'll see a lot of this kind of stuff later in the astrophotos that come up at the end of the meeting. In terms of visual targets, people were doing double stars, some of the bright globulars, which is a personal favorite of mine, the galaxies, those were all popular across all the nights. Also, there were some opportunities and learning moments. Several members brought their new telescopes out and their cameras and accessories and kind of got a chance to exercise them out at the Halo. So I want to just take a moment and talk about how awesome some of the HAL members are. It's just really an amazing group. It's fantastic. So first of all, I think I owe a big thank you to Ernie Morse. His commitment in doing, he ran all of these. He was the one that kind of initiated the impromptus for all of these. So that's a lot of commitment. I mean, he gets there, he unlocks the gate, coordinates the sessions, announces them, and he stays late to close up. And as a result of his efforts, we had 19 members enjoying nearly 13 hours of really good observing over the past month. So Ernie, hats off to you. That really kind of embodies, I think, the wonderful spirit that we see a lot of in HAL, of members really enthused about astronomy and trying to make it accessible to their fellow members.
Well,
And then
thank you, Jim.
A shout out. Oh, Ernie, great. Thank you. Seriously.
Yeah.
I mean, that is just an awesome job that you did this past month.
Oh, thank you so much. I appreciate being recognized, and I'm happy to do it.
Great. So secondly, I want to point out Jose, who's in the audience here this evening, and he is our events coordinator. So all things kind of happening out at the Alpha Ridge, that's kind of like Jose's domain. He gave Mike a crash course in astrophotography, helping him set up a donated ASCAR refractor and basically guiding him to get his very first image of M101, which I have up here on the screen. So, I mean, I think that's just really wonderful that, Jose's out there. He could be kind of like, no, I'm just going to do my own thing, good luck with that. And this is Jose's nature. If any of you know Jose, he is very, very enthusiastic about trying to help people and kindle that interest in astronomy. So, and Mike apparently is trying to set up a program at a senior center, or can you tell me a little bit about that?
Yeah, hi. So Mike approached me roughly a little bit after the March public start party. I hosted that one, and he told me that he's initiating a program in his senior assistant community because a lot of people there used to work with telescopes before, and he wanted to set up something for them because they couldn't come to the public start parties, but they were enthusiastic, and he was telling them about HAL. So first we met at a cafe to plan what he could get. He told me that he had a budget that someone was donating for getting equipment, and we wanted to make it as simple as possible, but something that will allow visual and astrophotography as well, and that will be accessible for a lot of different objects. So we picked like a medium-sized refractor for simplicity, no collimation, no fixing anything. Then we got a mount that was reliable and good enough for that kind of equipment. And then we got one of the ASI Air cameras, the 585 Air in color, because it's so simple that it connects through Bluetooth to the mount. And the idea was to make it as simple as possible that anyone could pull their phone and start doing anything. And then he got all the equipment. He sent me the pictures of the boxes. He was very excited. And he told me, hey, when can we start learning how to use it? And Ernie called the start party, and I told him, hey, why don't we meet there? And we start like playing with it. And we rolled it in that day, and he took his first picture of M101, which is fantastic. No post processing. This is just a live stack. And it was a really nice night. He learned how to do the polar alignment, which is one of the most tedious things that we can do, but he learned how to do it. He learned how to install every single part of the telescope, how to put everything. And now he feels confident to start doing it at his new club with the senior community. But the door is always open. I told him, hey, whenever you need a refresher or something, I'm happy to pop by. Is like 10 minutes away from my house, so it works out pretty well for me and for both.
Awesome. I really admire that. Thank you so much, Jose.
Hey, Jim, sorry to interrupt. This is Victor. When other speakers in the room speak, could you perhaps ask them to move a little closer to the microphone?
Okay, we'll have them come up to the front. Maybe that'll help. You hearing me okay?
Yes.
Okay. Okay, so what's up next? We have a member star party, which is obviously only for members of HAL this coming Saturday. I think the weather looked possible, that it might be okay. That should be June, not May. We have the public star party. And I'll just throw out here that we are looking to set up a time for a mentoring star party, which is specifically targeted for bring your telescope out, and we'll have folks out there who hopefully can help you if you have a particular problem or issue. It's like, hey, I'm having trouble polar aligning, or I don't know why, this eyepiece isn't working right or whatnot. It'll be a mentoring night. And so keep your eyes out on the HAL list. Hopefully you guys are on the distribution list. We have a Google group list where announcements like this get made. And if you are a member of HAL, hopefully you are on the specific announcements list. But at any rate, we are looking at doing this summer at least one mentoring star party to help those of you who have got new scopes. We are a member of the Astronomical League. The Astronomical League is a great group. It's basically amalgamation of astronomy clubs across the United States. They are having their convention, and it's going to be hosted by the Cincinnati Astronomical Society, so not that far, August 12th through the 15th. Program highlights are going to be a national convention with lectures, workshops, observing sessions, and vendor exhibits. I'm sure if you are into astronomy, that's a very cool couple days to spend out there. They will also have tours of local astronomy facilities. There's a Saturday night awards banquet, and you get to network with league members nationwide. The audience is amateur astronomers, educators, vendors, and outreach leaders from across the United States. So if you are interested, you can go on and learn more about this at alcon2026.org. And I will also, since I am a big ALPO guy, I will mention that the ALPO, which is the Association of Lunar and Planetary Observers, they are having their convention, but theirs is virtual. It is all Zoom and YouTube. It'll be July 10th and the 11th, Friday and Saturday from 1 to 4 p.m. in the afternoon. It's basically a national online convention. Actually, it's international. We get people from across the pond also involved. With talks, brief talks, they're like about 20, 30 minutes max on various aspects of solar, lunar, and planetary astronomy. Our keynote speaker, which I believe is Saturday evening, is Dr. David A. Kring, a planetary scientist known for his research on impact cratering and lunar geology. And he's going to present Exploring the Moon in the Age of Artemis, which is going to highlight the latest developments in lunar exploration and Artemis era missions.
Is there a cost to register?
There is no cost to register. It's free. The way that you would do is probably in another week or so at that link here, alpo-astronomy.org. There will be instructions on, you have to send a request to the convention person who's organizing it. He'll send you back the Zoom link the day before.
Gotcha.
And you can always jump on the YouTube channel. If you don't do the Zoom, you can always drop in on YouTube. So basically, if you're interested in solar system astronomy, this is a cool um, convention, and they will also be publishing this series of talks soon. Okay, so I'm going to stop my share here for a moment, and Dr. Vanderlei, if you want to come up and
I can probably share from here. And
so while he's working on that, tonight's speaker is Dr. J. Vanderlei Martens, Director of Earth and Space Institute at UMBC. And for more than 20 years, he's worked closely with NASA to develop advanced instruments for studying aerosols and clouds. He is the principal investigator for the HARP and HARP-2 sensors, including HARP-2, which is now flying on NASA's PACE satellite. It's the first U.S. hyperangular imaging polarimeter in orbit, giving us a new way to observe Earth's atmosphere. Dr. Martens has contributed to major NASA missions like MODIS, GLORY, and PACE, and his work continues to shape how we study our planet from space. So please join me in welcoming Dr. Martens. And let me see. Let's get this shared
you have
again.
to flick it. No, just okay.
So where were you?
Yeah, I'm sharing. They are seeing online. So
They're seeing it online?
Yes.
Okay.
You just have to. Okay, mix track.
We were seeing it. We're seeing your screen again, Jim.
Well, maybe stop sharing with mine.
Yeah, I have to stop sharing if yours. I don't know. Stop sharing.
Okay, stop sharing.
Do you see my screen again?
We see it. Yeah, we see your first slide now.
Okay.
Yeah, I just have to make sure they can see here. Usually you can swap the screen, but I don't see it here. Well, should I connect? Can I connect it here, my guess?
Yes, yes, yes.
Okay.
So,
Yeah, now I have to share that screen so that they can see the right screen. Can you online see the full screen?
It looks
Yes, we
great.
can.
We also saw all your slides a few seconds ago.
so you're seeing the screen at the moment from his presentation?
Slide number 1.
Yes, we are.
Okay.
Okay, so maybe.
Advance the slide to see if it's working.
It will. Just 1 second. Can you hear me well?
Yes, we can hear you fine.
Okay, so good evening, everybody. So I'm Vanderlei Martins. I'm a professor at the University of Maryland, Baltimore County, UMBC. There I'm the director of the Earth and Space Institute. And where, we basically, we work to produce, based on science questions, we will work on missions either on Earth or in space to measure either Earth or space sciences in general, like we do Earth and space sciences in general. My work in particular is with Earth. So I observe Earth, I work with Earth. Having said that, I have developed sensors to go and look at space, measure cosmic particles, or look at different objects. So it's our goal is really Earth and space sciences in general. So we work with students all the way from high school to postdocs, scientists all over the globe. And today I'm going to focus on Earth observations. I mean, that's my main science, right? So we take our telescopes and we point down at Earth and observe different types of sciences. And I'll focus in particular on what we call the HARP family of sensors. So HARP is what we call hyperangular rainbow polarimeter. So I'll tell you a little bit about that. So it's a family of sensors that we developed in my team for Earth and, for other planets observations in general. Before I go in detail on that, I want to give you just a little introduction on why we are doing it, right? So in terms of Earth, how do I get rid of that?
Drag it to the other screen or something.
I cannot even, okay, my mouse is here somewhere.
Go back
There
to the
you
Zoom
go.
screen. Yeah, there, you want to go over to more and then hide floating meeting controls. There you go.
Thank you. Need that one. Okay, there you go. So, I know you are into other planets and celestial objects. To me, Earth is the most beautiful planet in the universe, right? And has lots and lots of things, interesting things going on. Just to give an example here. So this is the dynamic of clouds, right, that we have in our planet, and all the clouds forming and dissipating and precipitating and moving around with all sorts of motions, cyclonic motions in some cases, or linear motions, whatever it is, and these clouds forming on and off all the time. But one point I would like to make, and I'll connect that later, is on Earth, there would not be a single cloud if it wasn't for particles in suspension in the atmosphere. Today we can call it pollution particles or dust particles or pollen. If you didn't have those particles in suspension in the atmosphere, there would be zero clouds on Earth. We just don't have enough water vapor in the atmosphere to form a cloud droplet on its own, like homogeneous nucleation of cloud droplets. So you need those particles so that the cloud droplets will form. So that's part of my motivation for the studies we're doing here. So this is now a map of the particles that you have all over the globe. So this is model, but it's a model based on measurements that we have done from satellites, measurements that we have done from the surface and with aircraft. So it's a model, but very based on the satellite. And from the satellite, we see the same thing. And you see here examples of particles, for instance, most evident. So you can see dust from the Sahara there that leaves the Sahara and can cross the Atlantic, right? It can travel all the way to the Americas. Megatons of this dust every year travel to the Amazon, for instance. And there are whole theories saying that the fertilization of the Amazon actually happens by this dust. So the Amazon soil is very pure on phosphorus, for instance. There is almost, very, very, the soil that is very pure. And the forest requires this phosphorus to survive. And you have megatons of material every year going from the Sahara all the way to the Amazon, bringing phosphorus and the other nutrients, right? And then you have things like biomass burning, right, that you have all over the globe, right, that the smoke can travel, again, very far, right? You can cross the ocean and go really, really far. And again, these particles are responsible for this interaction with the clouds. The same way that they're required to form clouds on Earth, they can destroy the clouds, or they can favor precipitation, or they can kill precipitation. They will modulate everything that happens with clouds on Earth. So that's my motivation, right? So we're developing sensors so that we can study this kind of phenomenon on Earth. And just for fun, give you here some examples of these particles, right? So dust, everybody knows dust. So the black dots that you see in the background, those are pores, those are holes. So this is a piece of plastic that has holes. We pass air through it, and we can collect the particles in the surface so that we can study these particles. So these are electron micrography pictures of these particles, right? So you see here 1 micron and 1 micron there in the scale. So 1,000th of a millimeter, right? Just to give an idea on the size of the particles. So dust particles have all sorts of shapes. They're relatively large compared to the smoke particles. And smoke particles, in this particular case, they're very spherical. different sizes, large variation in size, but very spherical particles. You know, you look at smoke, and many people think that they're looking at gases, right? People look at clouds and they think they're looking at water vapor. But guess what? Water vapor is completely transparent. It's invisible. We cannot see water vapor. The gases in the smoke are mostly transparent. If anything, some of the gases there would change colors of things a little bit, but you wouldn't see the smoke per se. What you're seeing are particles. What you see in the clouds are droplets, either water droplets or ice particles. What you see in the smoke are those little particles, right? So these are solid or liquid particles that you have in suspension in the atmosphere. We call them aerosols, right? And you have all sorts of aerosols, right? So it's the dust, the smoke that I showed you there, but you have pollen, you know, you have ash particles, you have sea salt that can be little crystals that can either be in the solid phase in the atmosphere, or they may have a lot of water around them, can be a solution. You can have agglomerates of smoke particles forming these soot clusters. So those are all things that are in suspension in the atmosphere. And we study them for many perspectives. One of them, as I said, for their interaction with the clouds. Another one for their effect on health, right? So pollution, health effects in general. Another one, if you're observing the sky, like you guys like to do, sometimes these particles are on your way. And, you know, for serious studies that people are doing, sometimes you have to remove the signal from these particles. So we need to understand what's in the atmosphere so that we can do the correction, remove the signal from that and study these objects. By the way, please interrupt at any time. Feel free to ask questions. This is very informal. I can jump in my slides. I can skip them. I don't really care. I prefer to interact. Like if you have any questions, please ask anytime. So we're studying these particles for many different reasons. I'll give you a little bit more example on the clouds before I go to actually what we do, just to give you a little bit more motivation, right? So I said that on Earth, there would be no clouds if it wasn't for these particles, right? So the way the clouds are formed, so you have these particles in suspension in the atmosphere. When the amount of water vapor increases and creates what we call supersaturation, so a lot of water vapor in the atmosphere, they will condense around these particles. And a droplet will be formed around every single droplet that we have there in the atmosphere. So the concentration of droplets you have in the clouds will be related to the concentration of particles that you have in the atmosphere. So if you have more particles, more droplets, but these droplets are competing for the same amount of water vapor. So if you have more particles, you're going to have smaller droplets as a result, right? And that's the case here at the bottom. So this is the case when the atmosphere is very hazy, you have lots of particles, the droplets will form the same way, higher concentration of droplets, but smaller droplets. Pristine condition, lower concentration of droplets, bigger droplets, the cloud will evolve and will precipitate more easily than in the case where you have pollution. So if you have more and more of these particles, more numerous droplets, but smaller droplets, the cloud keep growing and growing into bigger and bigger storms. And then by the time you hit the freezing point, right, where these droplets starts to freeze, the cloud developed into these monsters, right? So really, really powerful storms, really, really deep convective clouds that gets developed and that gets modulated by the number of particles, by the type of particles. Yes?
So how would the amount of particles in the atmosphere affect the formation of hurricanes?
So the question there is how the amount of particles will affect the formation of hurricanes. So these are actually things that we're still studying. Like we don't understand completely the interaction between these particles and the clouds or hurricanes. But there has been evidence of the effect on hurricanes due to dust, right, that you have over the ocean. I'm not an expert on that, and I wouldn't be able to tell exactly how they are affecting it, and I don't think our community completely understands it. So these are things that you're still studying. Like for instance, dust particularly, right? So when you have the dust particles, they not only can behave as a cloudy condensation nuclei and form droplets around the dust, but even more importantly, the dust is a very good what we call ice nuclei, and will help to form the ice in the cloud, which then can feed thermodynamically the whole effect that you have in hurricanes and some other clouds. So it's transition of phase, right? So going from vapor to water, from water to ice, or then evaporating. So those are all, it's kind of a thermodynamic engine that we have in the clouds, that we have in hurricanes, that feeds it, or in some cases can destroy it completely. Yes.
It's estimated that there's 40 to 50 metric tons of micrometeorites and cosmic dust that float through our atmosphere. Is that considered a major player in cloud formation? So
the question is if the micrometeorites that are in, very abundant concentration, if they are a major player in this kind of effect. They are a player, they are not a major player, right? So the concentrations that we have from particles coming from the surface is much, much bigger than that. But they are definitely a player. Now, the composition matters also, right? So a better, we call it cloud condensation nuclei, right? So the particles that will form cloud droplets. So if it's a material that's soluble, so that will be a better cloud condensation nuclei. And I would guess that most of these micrometeorites, I mean, they're like inorganic material, right? And they're not soluble, and they will, they have less effect as a cloud condensation nuclei. They are probably very good ice nuclei because of the structure that they have that's more similar to the structure of ice, like the microstructure, the crystalline structure I'm talking about, is more similar to the structure of ice than organic material, for instance, or biomass burning particles. So they may play a bigger role in terms of ice nuclei. But again, I would guess that their concentration is still much lower than the concentration of the particles we have on Earth.
So would the size of the droplet be an indicator of the amount of pollution in an area, for example, in the atmosphere?
So the question is if the size of the droplet is then an indication of pollution in the atmosphere. In a way, yes, but I'll give you an example. When we look from space, unfortunately, I don't have any picture here, but when we look from space over the ocean and we see the clouds over the ocean, and in some parts of the ocean, you have what we call stratiform clouds. So these layers of very flat clouds. If you have a ship under the cloud and the smokestack from the ship, right? So it's producing pollution that's going to the cloud. We can see that in the cloud because there will be a trace of much smaller droplets. Wherever the smoke is, there will be much smaller droplets than in the surrounding. And by the way, that's called the Tomney effect. So I was going to ask you if you invented that effect. No, I know the guy who did, but it's called the Tomney effect. That's exactly the effect of these particles competing for the water vapor and producing smaller droplets. So we can see that from space. I mean, we can see that. We can see that when we go and fly inside the clouds and measure those things. I wouldn't use that as an indication of pollution, but it is there, right? And we can see it.
It caught my attention because I am from Guatemala, and over there, water droplets are huge.
Yep.
And my brother sent me a video last time of rain over there. He said, in case you forgot. Yeah. And it is like these huge droplets. And here is like very small droplets. So I was wondering.
Yeah, I mean, pollution is one of the drivers, but there are others, right? So there are other drivers that are not just related to pollution. In fact, our community for many years was divided into people that saw aerosols was the most important climate effect, and because it has all this effect on clouds, and the others that, no, it's all about dynamics, right? So the dynamics of the atmosphere and aerosols plays a minor role. We know now for sure, we have plenty of evidence showing that aerosol has a major role in all this, but there are other effects that would make a rain in the Amazon or in Guatemala, much bigger droplets. So not only pollution, but this is an important effect. It modulates these rains, right? And cause this effect. So that's the motivation. So that's what I have been studying, right? So we have our telescopes looking down, or sometimes we have our telescopes looking up, just like yours, but we are looking at the atmosphere. Like we have telescopes that will point at the sun, and then we will make a circle at the same zenith angle as the sun. We'll make a circle and look at the sky. Because by measuring the scattering, the light, solar light scattered by these particles, we can measure the properties of these particles. And I'll show you that in a moment. So we have developed a series of instruments that we use for measuring this kind of phenomenon. So again, I'm interested on clouds on Earth, on aerosols on Earth, or in other planets, right? And how they are affecting the whole energy balance of the planet. Like by, once you have these particles in the atmosphere, you have, or clouds in the atmosphere, you have solar light arriving. Solar light will reflect from the clouds back to space. That cools the planet. Now, some of these particles absorb light, like you may have heard of soot or black carbon, or this, or you look at a smokestack from a truck and you see that black smoke coming out. That means that smoke is probably absorbing light, absorbing a lot of light. So you have particles in the atmosphere that absorb solar radiation. It will warm up the atmosphere. It may not warm up the planet, but will warm up the atmosphere at least, and will cause thermodynamic effect on clouds and in the atmosphere in general. So we designed a series of instruments, and today I'll focus mostly in two of these. So we call this the HARP polarimeter family, and I'll tell you a little bit about that and show you a little bit on what we have done. So the first thing is a small satellite. So that's actually the size of the satellite. This is just a model that I'm holding there, but this is the original size of the satellite. So we developed this satellite in collaboration with Utah State University and NASA, and I'll show you some more details, but we launched the satellite to space, stayed in space for 2 years, observing Earth, measuring clouds, measuring pollution, but even more important, demonstrated this new technique, the new technique on how we can measure these things from space in great level of detail. And if you are not familiar, right, so we work a lot with NASA and with other space agencies, but there are lots and lots of satellites up there, right? So this is actually now a small sample, because today there are so many commercial satellites that actually bothering you in your observations, right? There is so many of them there. But those are the ones, you see the ones around the Earth, some of them that we use for Earth science measurements, others for solar physics, for planetary physics, space physics in general. So there are many, many of these satellites. Actually, these are the CubeSat ones. Sorry, I forgot to say that. Small sats and CubeSats. CubeSats are these small satellites, right? They start at a cube of 4 by 4 by 4 inches. That can be a full satellite. Ours was, we call that a 3U. So it was 4 by 4 by 12 inches. So literally this size. And it's an autonomous satellite, right? That we will launch in a rocket, we'll go to space, and from the ground, we can control how it's pointing, we can acquire the data, send the data back to the ground. So these are a collection of other CubeSats or small satellites, and this is relatively old, it's changing every day, right? But just to give you a sense that there are many of these up there, right? So, and luckily my team is really fast. So we can work very efficiently, very fast. That's what the government wants to do today, we can do it. So just need them to keep funding us. But this was actually at Utah State University. So what happens is my team here at UMBC, we developed the payload because I'm interested in the science. So we're focusing the science. So we have science questions. We developed the payload, the instrument that will do the measurements. We developed the science behind it. How it takes to do a measurement for us to be able to observe things from space. So we developed that sensor, right? Sensor is about half of the satellite. So you saw the size of the satellite, a loaf of bread, more or less. So half of that is the payload, half of that is to control the spacecraft. Yes?
So what type of orbit do these satellites typically have?
So what type of orbit the satellites have? So we do all sorts of orbits, right? So this one in particular, so the HARP CubeSat, we launched that in the International Space Station orbit. So that's what we call an inclined orbit. Fortunately, I had a slide with the orbits. I took it out. But several of our satellites will be in a polar orbit. It's easier to explain. So polar orbit will be an orbit that will go from the South Pole to the North Pole or from the North Pole to the South Pole, but more or less going around the poles, around the Earth and crossing the poles. And then, it takes about 1.5 hours for the satellites to go around the Earth, right? So we do that about 15 times a day. right? So we go around the Earth about 15 times a day. And either will be a polar orbit, like I'm saying, so going around the poles. It could be an equatorial orbit that will be around the equator. And then you have inclined orbits that are in between. So in between the equatorial orbit and the polar orbit. So again, this one was the International Space Station orbit. So it's about 60 to 57 degrees from the equator, right? We call that an inclined orbit. We launched it in, actually, it's a small satellite, but we actually launched in a very big rocket. So this one was launched from NASA Wallops. This rocket was going to the International Space Station as a resupply mission. So they were bringing 4 tons of material for the International Space Station of supplies, including our little CubeSat. And once it's there, right, once it hits orbit, so parts of the rocket come back down or burn in space. And then you have, in this case, we had this Sirius spacecraft that you have here, right? That's actually the spacecraft bringing the supplies to the International Space Station. It's grabbed by the Canadarm in the space station, and then it docks this spacecraft at the space station. They got all the supplies, including our little CubeSat. And then
and the snares.
Oops, we don't need that. And then an astronaut in the ISS will handle the CubeSat, will put that in a compartment that then is, basically is a spring-loaded system that will shoot these little satellites like torpedoes from the ISS. It's literally a little spring that you have there. So it's this compartment that he opens from the inside, puts the little satellites there, close the compartment, and basically release it to space, like what you're seeing there. And once it's released to space, it's completely autonomous, right? So now we control it from the ground. You have the ability to point it, right? And to collect data the way we want, the way we need for our science.
So how do you accomplish the pointing? There are no thrusters on it, or how would you do that?
So there are all sorts of systems in these little satellites, and this has been developed over the last, let's say, 20 years. And from the beginning, they had no thrusters, they had almost no way to control, and then things evolved over time. So today, the satellites can have their own thrusters if needed. CubeSat, we did not have any thrusters. So the way we controlled it with these gyro wheels, right? So you have torqued wheels that we call. So wheels in 3 dimensions, three wheels that you have inside the system, that by spinning these wheels, you control the orientation of the satellite. So basically by conservation of angular momentum, right? So as you turn the wheel in one direction, the satellite wants to go in the other direction. And then by having 3 of these wheels in different orientations, you can precisely control how you're pointing. So a little satellite, like it is our satellite, had what we call a star camera. So had a camera looking at deep space and looking at the stars, and had maps of stars inside. So it's processing that in real time and determining exactly where we are pointing. So it has a GPS, so we know the location of the satellite, and then it has the star sensor to, again, look at the star field and determine which angle we are pointing. Also has a solar sensor, so that you can see the sun. When the sun is in the field of view, you can see the sun. And we use the stars and the sun and the GPS to determine exactly how you're pointing. So you can point to the ground within, let's say, 100 meters, even with a small satellite like this. And some of them are even more precise. So now you have more and more precise systems. Now, we do measurements of, the color of light, wavelength, right? So probably you're familiar with wavelengths. So we measure different wavelengths. We measure different angles. And I'll show you that, right? So you get more information by looking from different perspectives, different angles. And we measure different polarizations. And I'll tell you a little bit more about polarization, but that gives a superpower, right? So superpower of this kind of satellite. Like if you look at a cloud or look at a scene from space, right, that you see there on the left-hand side of the screen, you see a regular cloud, you see the ocean, you see land. Right, and then on the right-hand side is the same scene. If I look now in terms of polarized light, so I call that the alien eyes, right? So if I have alien eyes that can allow me to see polarization and colors the same way as we see colors in intensity, but now with polarization, what would I see? And that cloud that you have there in the left now looks like this beautiful rainbow. There's this very nice rainbow there in the center. I can barely distinguish the ocean from land now, because land is dark, the ocean, depending on the angle, is dark too. So the scene is completely different. And that's what gives us some superpower of interpreting what we are looking at, because by looking now at these signals that are different than the intensity signals, we can tell a lot. I can tell the size of the droplets inside the cloud. I can tell the size of the pollution particles that we have in the atmosphere. Particles that are like, 1 micron, half a micron, 0.1 micron. We can measure that all the way from space by looking at this polarization signal, by looking at the different wavelengths, by looking at the different angles. So it really gives us a lot of ability to discriminate what we are looking at. So we don't call this a rainbow, even though it's the same physics as you see from the rainbow. It's exactly the same thing. This does not happen from raindrops. So it's not a rainbow. It happens from cloud droplets. So it's a cloudy ball, not a rainbow, a cloudy ball. It is different, right? Because you cannot see a cloudy ball with your own eyes without polarization. It is there. It's a pretty strong signal. It is there, but it gets swamped by what we call multiple scattering that you have from the cloud droplets, right? It is there. Polarization will filter it, throws away the multiple scattering. Now I can see the signal very, very strongly. Now, this is the same thing, right?
Question?
Yes.
Is is it a linear polarization, horizontal, vertical? Do you change? Do you get, do you ever consider circular polarization or anything like that?
Yes, all of the above. So it is linear polarization. So in this case, we are measuring linear polarization, and horizontal, vertical, it's actually the total amount of linear polarization. So that's what you're seeing here now on the scene, like on the left-hand side. On top is intensity, one wavelength, one color, right? Just grayscale. That's intensity. And at the bottom is polarization. So it's degree of linear polarization, the total amount of linear polarization at any angle, right? So that we are doing here. Could be horizontal, vertical, so at any orientation. So it is showing here the total amount of linear polarization. And I'll tell in a moment what linear polarization is, but circular polarization, most of the particles in the atmosphere will not produce circular polarization. The signal is tiny. You get circular polarization from biogenic particles, from pollen, from particles coming from trees, right? So organic particles in the atmosphere, but most of the particles are not organic, so the circular polarization signal is very tiny. Clouds almost have no circular polarization, so we focus on linear polarization, that the signal is pretty strong. And if you look there, you have, that's why we call cloudy bow, right? Because actually it is a circular pattern around the backscattering of the sun. And if you put that in 3D, it will look like a ball, right? So if you take the brightest of those rings, it will look like a ball. Now, if I take those rings, that pattern there, and they do a cut, a cross-section, you have these oscillations. So if you find my mouse, so if I do a cut here, like a cross-section here, I'll see something like this, that has these oscillations. And it's by measuring these oscillations that I can tell the size of the particles. So you can see here, if the droplets are 9 microns or 10 microns or 11 microns. So this is a model showing how these peaks will vary. Like the distance between the first peak and the second peak will vary as a function of the size of these droplets. So we can really measure these droplets from space with really high accuracy, all the way from space. Lots of details here. I'm not going to focus on the details, right? But that's
Another question, sorry, if it's okay.
Yes.
Does the nature of the particle, I mean, if you have spherical particles, will they result in polarization like this, or do they have to be high aspect ratio particles?
So for polarizations like this, they must be spherical. So this polarization that you're seeing here only happens in relatively spherical particles and smooth particles. That's why water droplets are perfect for this. That's why in water droplets, we can see this very, very well. If you have particles like the dust I showed that is not spherical, they have the opposite effect. So those particles will produce depolarization. So what we do, like if I send a laser light in the atmosphere, and we do that, we call that a LiDAR, right? You hear LiDARs for cars today and for robots, but we have been using LiDARs for tens of years for probing the atmosphere, right? Where we send a laser beam and we measure what comes back from that laser beam. If I send a laser beam that's polarized, if the particle I'm observing is non-spherical, like a dust particle, that will scramble that polarization. The signal that comes back is not polarized. So non-spherical particles will have the effect of depolarize. So we actually use that to measure the shape of the particle. So informations that we get from these are size of the particles, refractive index of the particles, shape of the particles, smoothness on the surface of the particle, how rough is the surface of the particle. And I'll show you a little bit more of this in a moment. But then back to HARP CubeSat, right? So we launched HARP CubeSat. It's a pretty tiny satellite. This was now, 15 years ago when we started designing this, maybe 20 years ago when we had the idea. So technology there was just being developed, right? So, and our goal was NASA funded us to demonstrate this ability to do these measurements from space, that we could do these measurements in this very, very small mission. HARP CubeSat was the first US polarimeter in space looking at Earth. We have had one in the past looking at Venus, if I'm not mistaken, but HARP CubeSat was the first one looking at Earth from the US, right? It's the first one who has the ability to measure the clouds the way I showed, like what we call hyperangle. That's why the H on HARP, the hyperangle. It's the first satellite ever to have the ability to do hyperangle measurements from space. So in 2 years, we collected the amount of data that you are seeing here. It took us 2 years to get this collection of data because of the resources, right? To have this tiny satellite in space. We're trying to operate, we're communicating with it. And of course, we launched it right during COVID, right before COVID. And then COVID comes and we're stuck, right, for several months with the satellite there until we can communicate and get data. But, we got images all over the globe. So we demonstrated the technique. Things worked very well. Thanks to that, we got funded to build the second generation, so HARP 2. And HARP 2 now is a little bit bigger. So you see the scale here I'm the scale, but you see the model here in the background. I wish I had a better looking model, but I'm the one there in the picture. And then you see here the HARP sensor, right? It's this yellow thing here. So the HARP sensor there. So you have an idea on the size. This is the spacecraft now. So I have a little bit more resources than my little CubeSat, right? Because now I have this spacecraft that has huge solar panels that are not shown here, that has, huge batteries, has really good antennas for communicating to the ground. I can downlink a lot of data. Has this other instrument here. This is the other payload that's built by NASA Goddard. So it's the OCI, Ocean Color Instrument. So this mission is to look at Earth's oceans and get a lot of information about ocean ecology. Unprecedented measurements. We have huge amount of data now that we never had before, thanks to this instrument. And then we have HARP 2 there measuring clouds and aerosols. And then there is another instrument behind me that's also polarimeter built by Airbus and by the Netherlands NASA. And
Your phone.
Yeah. Just to give an idea, so someone was asking about orbit before. So that's the orbit that we have for the PACE satellite. PACE satellite is the one I just showed you, right? So you can see there how PACE orbits Earth. So it's a polar orbit. And then we have the three instruments. So we have the ocean color instrument, that's a spectrometer. We call that swath, so it has very wide swath. It goes back and forth is to avoid reflection from the ocean, the sun glint, solar reflection from the ocean. That's why it's going back and forth. Is the first sensor doing that. And then the swath is the width that you see there. Now you see HARP 2. So HARP 2 is what we call hyperangle. So it has several angles that we'll be observing an object. And I'll tell you a little bit more about that. We have up to 60 different angles. So every time we're flying, we see a cloud, we'll see that from 60 different perspectives, the same cloud. And then you have SPEX-1, that's the instrument from the Netherlands that I mentioned before, that has a very narrow swath, 100 kilometers. So you'll see what the effect of that is in a second. So with HARP2 and with OCI, we'll cover the whole Earth in 2 days, right? So in 2 days, you have full coverage of Earth with OCI and with HARP2. But SpaceX-1, because it's a very, very narrow swath, you have that line, right? So for every orbit, you have a narrow line, and then the next orbit 1.5 hours later, and then the next orbit. So you don't cover the whole Earth, right? So you really get like these small swaths of Earth during every orbit. But with HARP2 and OCI, then we get about, more than half of Earth. So every day, right? And then in 2 days, you close the gaps. In 2 days, we'll have full coverage of Earth. And I'll show you more of that in a moment. Now, what do we measure, right? So what we are looking at. So we'll look at different colors, as I said. So HARP2 in particular measures, if you are familiar with wavelengths, so we measure in the blue at 440 nanometers. We measure in the green, the visible light spectrum, right? We measure in the blue at 440 nanometers. Right here, we measure in the green at 550. We measure in the red at 770, or more or less here, 770 nanometer. And we measure in the near infrared, that would be here, at 870 nanometer. So those are the wavelengths. We have 4 wavelengths. And wavelength, right? So if you're not familiar with that, it's like, imagine a rope that you are oscillating the rope, right? It's the distance between the peaks of your oscillation that you have in the rope. So we're trying to represent that here, right? You have short wavelengths, gamma rays have very, very short wavelengths, and then next X-rays, ultraviolet, visible light, near infrared, shortwave infrared, microwaves, radio waves, so on and so forth. And basically the size of the waves, right? So the distance between the waves. I'm emphasizing that because that's how we measure the particle size, is by the relationship between the wavelength and the particle size. So that's how we get this information from space. So that's why we have one of the reasons we have multiple wavelengths. Now we do measurements on Earth over the whole spectrum, right? So we do gamma ray measurements, X-ray measurements, ultraviolet, all the way to microwaves for clouds, right? To radar and passive microwave measurements. We basically, for Earth science, measure the whole spectrum, depending on the application. And then we look at the relationship of the size of our particles. Like if you look at raindrops, for instance, so they can be millimeters to centimeters, right? So cloud droplets will be, 0.02 millimeters or 20 micrometers, all the way from 5 to, let's say, 30 or 40 micrometers. And we're going to look at the relationship of these sizes, the size of cloud droplets, the size of aerosols, pollution particles, and the wavelengths, right? So we're really looking at the relationship between these two things in order to determine what the particles are. There is a huge fleet of Earth science satellites. Now I'm focused on Earth, and these are now larger satellites, much, much larger, like PACE, for instance. So PACE is here somewhere in this list. PACE is here, somewhere in this list where HARP2 is, right? And we are measuring all sorts of things, right? So we have some of these sensors measuring the ultraviolet. So some of these instruments measuring from visible to thermal infrared. Some of these are measuring microwave, either by having an active radar, an active system producing the microwaves and measure the reflected back, or some that we call passive, like Earth, objects on Earth, clouds, the surface. They are all emitting microwaves. They're emitting thermal infrared wavelengths. So we have sensors observing that. And with that, we can characterize lots of things that are going on Earth, right? So lots and lots of details. Again, my science is mostly aerosols and clouds. I focus on those, but we are measuring all sorts of things, right? There are all sorts of systems. So just to give you a sense, so this is again the PACE satellite, HARP2 instrument there. So you have another person here as a scale, so for you to have an idea. So it's a pretty large satellite, right? That gives us these resources to do all the measurements, do these global measurements that I'm talking about. One curious thing is when you're going to put something in space, anything, you have to make sure you will survive, right? So it has to survive the radiation that you have in space, right? You have to survive the launch, which is pretty intense, right? So you have the vibration that you have during the launch, that, you know, if you're not very careful how you design something, it will break before it hits orbit, and I can't fix, right? Once we send to orbit. So you have to make sure these things will work. So we do lots of tests in the lab. So we test it in vacuum to make sure everything works. We test it with temperature. Like as you're orbiting Earth, you're on the sunny side, things can get pretty hot, you know, very common to get ATC, you know, pretty hot. If you think that it was hot today, you know, 3 times the temperature or something like that, right? You go on the dark side, it can get very cold. You can go to minus 70 C. So minus 70 C plus 80 C, it will damage most of the systems that we have here on Earth. So you have to test for that, right? And by curiosity, so this is one of the tests. So this is a vibration test. So imagine we designed this thing for 10 years, we were working on this thing, right? For 5 years, we're fabricating every little piece. And we are taking care of every little detail and then we take it to this vibe test. My team is there crying, right? What are you doing to my baby, right? So it's like we treated this thing so carefully. Like for this thing to travel from UMBC to NASA Goddard, we rented a disability van because we want to use the elevator of the van to lift it very, very carefully. We didn't have money to do the same thing as NASA does, so a disability van worked very, very well. And then we take it there and they do this to our instrument, right? And then what happens? He was completely destroyed.
Oh, no.
I had a heart attack that day. So we did this test for 3 days. This was 3 days of tests, 3 full days of tests. And the last day, I'm so confident. I stayed in my office because I had work to do, and I'm monitoring it remotely and listening. And then I just hear, okay, we're almost done. We have an extra 30 seconds of tests to do, 30 seconds after 3 days. We have another 30 seconds and we'll be done. So this is what happened in the last 30 seconds after 3 days. So what happens is, you know, you design for this, but we model what was going to happen during launch. And we work with experts that help us to do all that modeling. And the loads that we get, you know, how much force it is going to suffer, you know, the test they did was 10 times stronger than the load we designed for. It was 10 times. So this would have survived the launch. Would have been no problem. Would have been in space. We'd have no issue at all. But the test was too much, right? Then we had to do a full investigation on what happened, why that happened. We learned, we understood it very well, redesigned it so that it would survive with no problem. 6 months, we recovered fully. They said it was a record, like an instrument that's completely destroyed, and we rebuilt it in 6 months. To the date, it was exactly 6 months. We were back there doing tests again. For that one, it stayed there all the time. I never left. And it survived, right? So no problem. It's in space now for 2 years. We've been collecting data. Another curiosity, like when you do a payload like this, either for space sciences, for earth science, you need to understand very well what your instrument does. You have to understand your telescope very well, but if you're doing observations like you do and you're taking pictures, if you're not doing quantitative work, you still want the best instrument you can have. But if I want to measure particles from space and know the size of those particles with a precision of 0.1 micron, I need to really understand my measurement really, really well. So what we do is we calibrate these things extensively. Again, my team is very fast, so we can do that very, very efficiently, but this is my team doing it at NASA Goddard, right? And you can see the different colors of light that you're generating, so we know exactly the color of light you're generating and the amount of light you're generating. We know exactly the wavelength, and we use that to characterize. So it took us about, I think this was about a month of work, very intensive work. We collect about 1 terabyte of data, really characterizing things in a lot of detail, right? So that when we launch to space, we know exactly what we are measuring and what we are observing. So as I said, right, so we get Earth in 2 days. So this is 2 days of data from HARP-2. So we cover the whole Earth. Right, 1 day you have gaps like you see there on the left, You have little gaps. And then in the second day, you go and you cover the gap. So in 2 days, we cover the whole Earth and we can observe it in great detail. I told you before about the alien eyes, right? So the polarization measurement. So this is Earth in intensity from HARP2. This is Earth in polarization. So it's a completely different planet. Like that's why we call it the alien eyes, right? So you're seeing things now completely different. So for us, that's information. So we are seeing different wavelengths, different polarizations, different angles. So as I said, HARP observes something from up to 60 different viewing angles. And on the left there is an example of that, right? So if you observe that cylinder with just one angle, if you observe it just from the top, you see a circle, right? That you have there in the center. Now, if you observe from different geometries, different angles, you can tell what that cylinder is in a lot more detail. So we use that not for macroscopic objects, but for really, really microscopic objects, right? So like these tiny particles. By measuring all the different angles, that's how we can tell the size, shape, and a lot of information about the particle. Another example, right? So if you look from one angle, you have the figure there on the left. And what is that? Does anyone can guess what that figure is?
Like a whale.
A whale?
Goldfish.
A goldfish?
A shark?
A shark? You're all wrong. It's a bird. So if you look from one angle, you can't really tell, right? So one angle, one wavelength, we wouldn't be able to tell what it is. So we need the perspective, right? That's why HARP2 has all these angles that we have here. And then from all those angles, we can really tell in great detail what you're observing, right? So this is an example of 90 angles that you have here with the colors in this case, observing a dust plume. But then from analyzing this data quantitatively from all these different angles, we can tell a lot of information about the surface, a lot of information about the atmosphere. So the goal of HARP2 on PACE, the main goal was actually to correct the atmosphere, to remove the atmosphere so that they can study the ocean. Like the goal for you, if you're observing the sky and you have things on the way and you want to do quantitative measurements, you have to remove the atmosphere. We can do that because by studying the scattering of these particles, we understand enough the atmosphere that we can remove that with our calculations. Yes.
So to get those different angles, you're measuring as you go around the orbit. So at different times around the orbit to get the different perspectives. Do things change over time?
Yeah, that's exactly right, right? So the way we get the angle is our sensor has very wide field of view, 114 degrees field of view along the trajectory. So very, very wide field of view. So when the satellite is coming, right? So if you take one point on the ground, I have to find my mouse. You take one point on the ground here, the satellite is coming, my forward view is seeing that point on the ground already and images that point and keeps imaging continuously. Then satellite moves, right? Now I have another angle. So that other angle will observe that same point on the ground, another angle. So we do that 60 times, right? Continuously. It's continuously happening. So between my forward angle and my backward angle, that will be all the way there, I think for HARP2 is about 6 to 8 minutes. Yes, things change in 8 minutes. A cloud can change very substantially in 8 minutes. So I'm going to miss that, lose that, right? That is the only way I could do that instantaneously if I had multiple satellites. And we are looking at that. So we are designing our constellations of satellites, having several looking at the same object simultaneously so that we can get those angles at the same time. But there are things that don't change that fast, like the aerosols don't change that fast. So I can still measure aerosols very, very well. In fact, what you see here, so this is intensity. So the same signal as you see with your eyes in the red, 670 nanometers. This is a function of angle. I'm plotting here as a function of angle. So you can see these are measurements as a function of angle. So you have here 60 different angles for intensity, and this is for parameters of polarization. So you see that this figure, this is for the same point on the ground, right? 1 pixel on the ground. And you see how these functions, these curves are all different from each other. The black line is our model, like we fit a model to it, a mathematical model to it, that once we get a good fit, like you have here, you have the experimental, the red points are the experiment, the measurement, and the black line is the model. Once we fit that model, we can understand what the particles are, what the surface is. Like this is a real example now from HARP2, that particular pixel. This is how it varies as a function of angle for the different wavelengths. I said the blue, the green, the red, near infrared. I don't know. I'm not gonna bother you with the physical details here, but we do that so that we can obtain things like this. So this is now smoke from the Amazon, and I can measure the amount of smoke, right? This is a map now of the amount of smoke with high accuracy that we have, optical thickness of the smoke. How much of that smoke are in very fine particles, less than 1 micrometer particle? Most of the smoke. Remember the lateral microscopy that I showed you, that the smoke the smoke particles were less than 1 micron? I can see that from space. Here I'm measuring the size of that smoke, less than 1 micron, and I can tell what the size is. If I look at large particles, almost nothing. There are some large particles here, but almost nothing. So I can tell that. I can tell how much those particles are absorbing light. I can tell the height of those particles, how high they are in the atmosphere, and so on and so forth. So we get lots and lots of information from these particles. Our goal is to do these global maps, right? Mapping these particles, determining what they are. Since we can measure refractive index, we can tell this is a dust particle, this is a smoke particle, is a pollution particle, sea salt, so on and so forth. So just a couple more minutes just to give you some more examples, but this is what we do from space, right? With the sensors, and we can measure things with great level of detail.
So just a question on
yes.
that. Since you're looking at dust and smoke and everything else, where's the best place to put a telescope?
I don't know. Someone here in the audience is interested in looking at the sky, it looks like. I'll tell you where the best place is. I'll tell you where the best place is. Because we've been there. I'll show you. It's some of my next slides. This is the best place for you to put your telescope. So this is one of the best places, right? This is in the Andes, and you have here Lake Titicaca in Bolivia, and the Salar of Uyuni. So the Salar this is hundreds of kilometers of salt, flat salt that you have there. And then this lake, right? Both at about 4 kilometers altitude, right? And we went there not to put a telescope to look up, but it was a really good place, and I can show you some pictures that we look at the sky from there. We went there so that we can calibrate our satellite, right? We can look at signal from the lake and signal from the Salar, and now compare with the measurements that we do from space. So this is the Salar. So again, hundreds of kilometers of salt, right? So very homogeneous surface. And this is the lake, right? So we had a boat, and we went there with our drone, where we built a polarimeter similar to the one we have in space, and we put that in the drone so that we could look at the surface and compare with the measurements that we were doing from space to calibrate, right? And you can imagine, right? We're, again, hundreds of kilometers, and we're in the middle of this thing. Luckily, the car didn't break, because if it did, I wouldn't be here today. Well, we had 2 cars for that reason, but that's a great place for a telescope. I mean, look at the sky. Right, so it's and then you can see some of the pictures with the cell phone. Wow. So I have an answer for your question.
That's great.
And you can see there our drone, right? So collecting some data there. Yes.
But do the salt particles salt particles that are probably blown into the air there not serve as like particles for the clouds to?
So if you had salt particles that would be blown to the air, yes, there would be pollution in the air. There would be aerosols in the air, right? Those salt particles are very attached to the ground. It's a little bit humid, the surface. So they're very, very solid. Like it's actually hard to get, so you have to break like a particle to take it out. So you can see how those things are. So there is almost no salt aerosols there most of the time. I'm sure there are times of the year and situations. So my goal actually would be to go there for the whole year, right? Once a month and collect how the surface is varying over time because it does vary a lot, and we are using this. We want to make this a calibration site for satellites, right? But one of my engineers, so Dominic, he's the one who took this picture. He does amazing sky pictures, right? And I'll actually tell him about your club, but he's the one who took these pictures there. But that's always the cell phone. So for you to have an idea how the sky is, right? So it's, and what you could get in those locations. So that's basically it. I have a lot of material, could be talking here forever. Just to illustrate, we also do these things from aircraft, right? So this is the NASA ER2 aircraft. So this is the old U2 spy aircraft. Also, you get amazing skies if you put your telescope there and take pictures from there. So the pilot takes picture for us with his camera, sometimes of the sky and the surface, and it's absolutely amazing. And we put your instruments in, we put a copy of the satellite sensor in this aircraft, and we collect data from the aircraft again to validate what we see from space. In fact, in August this year, we'll be flying over what we call pyrocumulus clouds, so clouds that are formed from smoke, from wildfires, to characterize those clouds that have a lot of smoke on them. And, you know, this one of my PhD students, so we have students involved in the project, so they will go. She actually, this year, she will be one of the flight scientists for this mission as a PhD student. Brent used to be my PhD student. Now he's one of the scientists working in our team, like integrating these instruments and flying them in the aircraft. So this is kind of an advertisement at the end here. Like, I have at least a couple younger fews here who could be interested in coming to us and work with us, right? So we have a whole program for this kind of measurements. Again, Earth or space, we do both, right? And so, thank you. Yes.
Question, what's your future funding look like? And this is going to be a hard thing.
Yeah, so actually we were building what we call Megaheart 4, not 3, but Megaheart 4, because it was a much bigger instrument. It's still small, but much bigger with a lot more capability, a lot more resources. We were funded to do it. And of course, it was cut because, you know, this kind of mission, this kind of measurement, you give too much information about Earth and our environment and all that. We're recovering some of those fundings. So some of the missions that were cut are being resurrected now. Unfortunately, they did cut us as a university from that project, but we are about to submit a proposal to NASA to bring back that sensor. And if we are successful, we'll be our own satellite with the sensor. We're going to be working closely with NASA, with many other institutions. So we are suffering a lot from the cuts. My team is at risk. So if I don't find something to keep my team by the end of this year, we will start losing our team. And we are already losing it because people see what's going on and they're like, okay, I want to have more job security, and they're going to other things, right? Luckily, my team is very versatile, so we're finding projects. We have many, many things coming, but we're having to be right now very, very creative. And some of the work we have to do has to be on the edge of military work to be able to be funded at the moment. So it's very, very tricky. Yes.
What majors are you taking for this kind of studies?
We are very multidisciplinary, so we take measures from all areas, like to understand, you know, Earth and the atmosphere. You need everything, right? So I have engineers from the multiple different areas. We have physicists, chemists. We need biologists to understand. We need to have a lot of ocean biologists to work with us in the PACE mission, because to understand the ocean ecology. We got at one point a psychology intern because we really needed it. So it's all sorts of measures, right? Mathematicians. So it's a very broad, like we cannot do this alone. Like you cannot do this from one discipline, right? We take everybody. People interested in modeling, in theory, in engineering, building things. So it's all sorts of people.
I'll probably ask you more information later.
Sure.
Were there any questions online?
I have one. Is there, this is just so cool to look at this graphic. Is there a resource online that you can look at historical, how this has changed over time, or is there
Yes.
a
There are lots of resources online, a lot of them at NASA websites. I can try to find some a list of resources and maybe share with Jim that he can share with everybody here. But yes, there are lots of resources. You know, many people don't even know that NASA does earth sciences, and it's a big mission for NASA, right? So looking at earth sciences, and NASA actually opened up the whole world to do this kind of things. Like when I started working in this area, if you wanted satellite data from a given location, you'd have to buy it, right? If you wanted so different data sets and all that, we had to purchase those data sets. And then NASA started with this policy of everything should be free for science, and they pushed that. Now the whole world is doing it that way, right? So I'm from Brazil, like even in Brazil, like if something done by the Brazilian Space Agency, it will be for free, like for free for everybody. So they will distribute for everyone. NASA started that, right? So NASA was the first agency of doing it that way. Europe now is booming, right? So unfortunately, we are retroceding a little bit here, like we slowed down a lot, but Europe is booming, right? They're launching mission after mission, and they are doing all sorts of measurements. You know, we have one polarimetry in space right now that's hard to. Europe is launching a series of them with a lot more capability than, well, not more capability, but different capability than what we have, and we're trying, right? So we're pushing here. India is booming on this area, starting to produce all sorts of data. They have all sorts of projects for the near future. But the answer is yes, there is a lot of resources on this. You know, NASA GIS, most people have not ever heard of NASA GIS. So that was one of the NASA centers in New York. It was completely destroyed over the last year, right? And literally, they took computers and put on the street because they had a month to leave the building. It was completely closed. So NASA GIS was one of the, the centers in the world that was producing data like this, right? They had the models that could really interpret what's going on. It's gone. Like, was completely destroyed. This one was done from Goddard, right? So it's from, but the guy who did this, who was forced to retire, is the guy who developed this whole system from scratch. Like, of course, there are many people behind it, but one of the people who envisioned this before everybody else, he just retired about 6 months ago. He doesn't want to retire. He's still going to meetings from his own pocket and participate. I was in a meeting with him 2 weeks ago, but he was forced to retire. So,
Obrigado.
Yes. De nada.
All right. Again, thank you very much.
I'm not sure what should.
Okay. So everybody online, are you back up with my slide deck?
No.
I need to do a share. That's what's going on.
Hey, Jim, make sure you share the main screen, not the slideshow screen.
Yeah, that's what I'm going to try to do here.
So if this is our website at the bottom, showing graphic, and you can find it. I'll send you the link.
Also, you have your background on, so all we see is we don't see the folks there in the room. Where's Wes when you need him?
I don't know. We're gonna fire him.
Sorry, guys, I had to watch my kids tonight.
That's no excuse. Bring him here.
They're 6 and 3. I don't know that super tired 6 and 3-year-olds are what we want, but I can.
Do you see it now, guys?
Oh, I don't.
We see it.
Yeah,
do
we
see
see it
Oh,
now.
yeah. Okay, now we
Yep,
see it.
looks
Okay.
good.
All right, so the SeeStar program, for those of you who don't know, we have a SeeStar telescope at HAL and we lend it out. So this month, Jeff finished up using it and Eileen took it. She was here earlier today and is using it. If you would like to sign up to use the SeeStar for a month, you can go to our website and there is the link there. And you can add your name. And I think probably right about now, we've got maybe 2 to 3 people ahead of you. But it is an excellent, it is very easy to use. I had a chance to use it back in December. It's really a fabulous AI type of telescope. Can do a lot of amazing things. All right, Wayne, you want to come forward and tell us what's up in space?
Okay, this is actually very much breaking news. A live stream on the internet this morning from, what is it, BaltimoreShipWatchers.com/live stream. They were live streaming things coming into and leaving Baltimore Harbor, and they caught the barge Pegasus, which is NASA's barge that's coming into Baltimore to pick up the Nancy Grace Roman telescope to deliver it down to Kennedy for launch on a SpaceX Falcon Heavy. And so this is a screen grab from their live stream. And so you can see the one tugboat in front. There's actually a second tugboat in the back, and then you can see the barge there. And I did stretch the live stream. This was about 4:17 this morning, so it's still dark. So I had to stretch it, use some of that astrophotography skill set, right? And you see what happens when you stretch a JPEG. So anyway, so this was the barge coming into Baltimore to pick up the Nancy Grace Roman telescope. The current launch date is August 30th. That's what they're aiming for. So I think I said last month it was no earlier than early September. Well, August 30th is the new early September. So hopefully it will get down to Kennedy and get mated to the rocket and get launched very soon.
Awesome. All right, so in terms of shallow skies for the next roughly 30 days, this is one of Mercury's best appearances for this year, and it is an evening appearance. So the way that things line up, evening appearances in late spring are the best because the ecliptic has a steeper angle to our horizon. So June the 15th, it reaches its greatest distance. So it'll be the longest period after sunset, the highest up. And the moon will be right next to it on June the 17th. Venus is easily seen in the west right now. It's that bright star. It's got a gibbous phase if you have a telescope. Not a lot of detail, obviously. It's just a white featureless globe, but it is still kind of neat and kind of like to see over time as the planet is swinging closer to us. You'll be able to see it growing in size, and it'll go from a gibbous to a half phase to a crescent. And so that's kind of neat to every once in a while. If you have your telescope out, check in on Venus while it's waiting to get dark. And the moon is close to it on June the 18th. Mars is in the pre-dawn sky. It's really very tiny, not very much to look at this point. If you're a photographer and you're into planetary imaging, you can probably begin to do some imaging with it. Jupiter just 2 nights ago, I think, was in a nice conjunction with Venus. Of course, it was cloudy here, but it's dropping quickly now, so it's going to be lost in the sun's glare very soon and will reemerge later in the summer in the dawn. Saturn is pretty much the main object. It's in the pre-dawn sky. Its rings are much better now than they were last year. As dawn begins around 4:30 in the morning, it's about 25 degrees high, so that's high enough that you should be able to see it. By the 15th, it's 35 degrees. Rather, by July 4th, it'll be 35 degrees. So it's definitely getting up there. And if you want to check it out, if you're an early morning person, I think you'll be pleasantly surprised that the rings are far more open and visible now. So on the 19th, we've got an interesting and somewhat rare event that's going to happen, which is basically a lunar occultation of Venus. It's going to happen on the afternoon of the 17th, and the moon will occult or cover Venus. It's, like I said, not a common occurrence. I'm seeing a lot of variability in terms of when it actually will disappear from our region. It's going to be roughly 3:46 in the afternoon. Now, the moon and Venus are both bright enough that actually you could probably see them if you kind of like shielded the sun behind something, like a building or trees. You could maybe see it with your naked eye. You can definitely see Venus with your naked eye. You just got to know kind of where to look. It's going to start off at that point at 3:45. It's going to be very high up, 72 degrees. So it'll be almost directly above you when the disappearance occurs. And the disappearance will occur along the dark edge of the moon. So it's going to kind of gradually, you'll see Venus kind of gradually being eaten away as the moon advances on it. Binoculars, small telescope, or I said even naked eye, but honestly, binoculars are probably the best thing here. If you have like a lounge chair and you can look up with the binoculars, that would probably be excellent. Reappearance, again, a little bit of discrepancy as to when that's going to happen. Seems to be about 10 after, and it's going to be at a position angle of 310 degrees. So if this is the crescent moon, you can easily see the Sea of Crises. It's going to be just above the Sea of Crises that you'll see Venus pop out, and probably take, I don't know, maybe 30 seconds or a minute or so for the planet to gradually emerge. And that's different than if you ever seen an occultation of a star, because that will wink out immediately. This, you know, it comes out and then it gradually increases until it's free of the limb.
Can you just confirm, I'm sorry, I might have missed it, but that says June 19th and June 17th, which is the correct date?
I believe it is the 19th. It is in, I'll have to double check on that. I'm pretty sure it was the 19th.
Okay.
Let me go back up if I can. Yeah, because the moon's adjacent to Mercury on the 17th. The 18th, it's below probably Venus. And so I'm thinking it's the 19th. But thank you for that discrepancy.
I've got Stellarium up, and it looks like it's the 17th at 15:07. What is that, 3 in the afternoon?
Let's put it, it is in Sky and Telescope for this month. For those of you who have Sky and Telescope, I think it's page 48. There is a link there to the International Occultation group, and they have a whole bunch of different cities throughout the Western Hemisphere here that are going to see that. So I will send out a correction on the Google group. Another reason to be a member of the Google group is that we are all on the same wavelength in terms of when this is going to happen. All right, and so then finally, what you might want to consider doing is an M13 challenge. M13 is a globular cluster. It's a magnificent cluster for those of us in the Northern Hemisphere. if you go outside and around 9:30 o'clock, when it's starting to get dark, look overhead, look up, and you're going to see a bright orangish star. That's going to be Arcturus. And then look down to the northeast, you'll see another bright star that's kind of white. That's Vega. And if you draw a line between those two, and you go roughly 2/3 of the way down that line, and with a pair of binoculars kind of sweep the area, you should be able to pick up M13. It'll look like a fuzzy star. You know, everything else, if you get a sharp focus on your binocular, there'll be points of light, but then there will be this one fuzzy little thing that's not quite pinpoint, and that is M13. If you have a telescope, that's of course, it's a little bit more challenging with a telescope because you've got a smaller field of view. But in terms of getting started, binoculars are a great way to begin to explore the night sky. And this would be one activity that you could do, would be to try to see if you can find M13 in the night sky. All right, so we're going to go on to our astro photos. Jose.
Oh, this is M13, the one we were just talking about a moment ago. It's the first time I ever take a picture of a cluster, so I was pretty excited, and it turned out pretty well. I never thought that I was going to get so many different colors in the stars. In the middle, I thought it was going to be blown out, and it turned out pretty well.
And what kind of a scope is this?
Oh, this is the Oscar B with the 80 millimeters aperture. It was 600 millimeters focal length, and I used the ASI 585 mm with RGB.
It looks great. Great job. So that's the object I was just saying, you know, you might try to find. Obviously, it looks a lot different in an image, and even in a telescope. You won't see that quite, you know, that kind of resolution. If you use averted vision, you'll see some of these stars pop out, depending on the size of your scope. And here is your M101.
Oh yeah, this is my submission of M101 for the object of the month for May. So yeah, first time I imaged this one too. It was a first time for both images. I don't know. I saw it before in other images, and I thought it looked funny, and I didn't want to try it. And this time I decided to try it, and I like the details. Looks pretty nice.
Yeah, it's a great spiral. Beautiful. And closer to Earth.
Ooh, that is my first light of the Lunt 80 I just got. Very excited to have that scope. Is phenomenal. I got very into solar imaging and solar observations now because of a Coronado PST that someone pretty much donated to me at the beginning of the year. And this is the very first one I took with the Coronado. I have a new one now that looks a little bit more crisp. I'm learning a lot on solar photography now, but I'm really proud of this one.
So you're not going to sleep anymore. In the daytime, you're going to do the sun. In the nighttime, you're going to do M13, M101.
I never sleep.
You never sleep. Okay. So Wayne, this is from, I think, last month.
Yeah.
This was the winning entry for the object of the month last month.
So this is M81 with my 8-inch Ritchie creation reflector from Alpha Ridge Park. It's 13 hours of exposure time. Yeah,
It's
say it one last month, probably for the month.
So how is a RC different than an Schmidt-Cassegrain?
The Schmidt-Cassegrain it corrects its spherical aberration with a very weak lens up front on the corrector plate. The Ritchie creation does not have a corrector plate. It's a different optical design it's a Cassegrain like telescope, not a classical Cassegrain. It's a different optical design that's mostly intended for imaging. It's got a very large central obstruction. The secondary mirror is almost 50% of the diameter of the primary mirror.
Wow. Okay.
So so it's made primarily for imaging. It happens to be the same optical design as a correctly configured Hubble Space Telescope. It's also a Ritchie creation. So yeah, it's just a different optical prescription.
Alrighty, well, that's certainly a beautiful result.
Okay, that would be me.
That would be you, Steve.
So this is me taking a SeeStar S50 and pointing at the Heart Nebula, and this is pretty much like the central core of the Heart Nebula, so I call it the heart of the Heart Nebula. And I use PixInsight and some other stuff. I don't remember, I might have used narrowband normalization at some point to on this. I don't remember, but it was fine. It was different, and I just like the wispiness in it.
It looks very nice.
Me again. So I recently acquired a Coronado PST telescope from our friend Jose here, and it's mine now. And this is me playing with this. I'm just starting to get into solar, so it's been kind of fun, and I'm trying different things out to see how to get different views of the sun. So on the left, I'm overexposing things a little bit and processing so that I can see the prominences coming around the edges. And on the right, not so much. So you see less, you can actually see a prominence coming off of the right edge, but I wanted to get more texture. And, I noticed that when I looked through the telescope and, the naked eye, well, not naked, I mean, through the scope eyepiece, I do see some texture, and I can easily see the prominences, but when you image and you processing the stuff, I can see more because I can adjust the contrast, especially if you do live stacking of while you're viewing things. And the stuff I see on the screen doesn't always translate well when I look at it on the phone. So I'm always playing with, I got to over brighten it. If I'm going to post this on like Facebook, people are going to look at it on their phone. So I have to brighten it more than I'd like to. I'd like it a little bit darker. So this is a little bit brighter because I know it's going to be on a screen.
Yeah, very
so
nice.
The one on the right, the one where you can see some texture. And it would be mine again. So this is a close-up of, there's a sunspot, there's a prominence off to the right from that, pretty much that same view that of the right-hand picture I just had, but you can actually see more texture to the chromosphere, and you see that prominence. I didn't bring out that prominence too bright because I wanted to be able to see more of that texture on the surface area of the chromosphere of the sun.
Have you caught any flares yet?
Nope, not yet.
Not yet.
Is that me again? Oh,
I
forgot about this one. Okay, so this one's interesting because this is another one where I was trying to get some of the prominences, and then I tried to stack a prominence close up. So overexposed everything, got the prominence, but stacking didn't work very well for me because if you look up closely at it, it's hard to see from here. There's a bunch of little squares that make up that prominence. So I got to work on that and learn a little bit. So this is kind of a learning, something I need to learn because this is more of a failure, but it's for me, even though it still looks pretty cool from afar.
I love your failure.
Yeah, thanks.
Really nice.
When I saw this, what it immediately evoked in me was the total eclipse from 2024. Remember that prominence at the bottom? Those of you who managed to catch the eclipse. I mean, that prominence there almost looks like it, except it's at the 7 o'clock instead of 5 o'clock position. That was so the great picture of a prominence there.
Thanks. I really like this PST. It's a very basic solar scope, but I'm finding I can do a lot with it. So I'm working hard with it.
And correct me if I'm wrong, but visually that's going to be more of a reddish color, right?
That is a reddish color.
So you're doing a really great job here, I think, in terms of kind of like evoking an orangish sun kind of color, how we would associate it.
And a lot of people capture the sun with a monochrome camera. I capture it with my planetary camera, which is a ZWO 678 camera, which is a color camera. And I haven't gone the monochrome route. So I start with the red and I have to pull this out. Had a little bit of training from Wes in how to pull out some of the colors.
Mhm.
And I've been applying what I've learned. And
Yeah, no, it's great. I mean, beautiful shot. All right, and this one's mine. Back in May, I had an evening. It turned out that the seeing wasn't so great. I was trying to get one more run of Jupiter in. But what I was able to accomplish is that I got it in 4 different filters. And with the great red spot out, I thought that was kind of cool because here in white light, you can see the red spot. There, you can see a little blue festoon hanging off the upper equatorial band. In UV, the red spot is much darker, of course, because a red object through a blue filter is going to boost the contrast and make it darker. Plus the fact it is absorbing materials, UV absorbing there. In IR, it becomes very light. You can barely see it. Almost looks like a hollow. And then over in the methane band, you actually begin to catch higher level structure cloud features in methane. And you can see in the methane image, which you can't see in any of the others, if you look up at the top part, there is a storm called the North-North LRS-1 that shows up. And so could only pick it up in that methane light. And that's partly because of the seeing. If the seeing had been better, probably could have picked it up in the white light in the IR as well. But again, that's kind of part of why I love Jupiter and planetary imaging, is that you can get a lot of different views and information by looking at it in different wavelengths. Okay, Wes.
Yeah, I took this with my Daystar Quark, which has a built-in 4x Barlow, so there's no full disk images for me. They're always close-ups, especially because I'm pairing it with a pretty small sensor. I actually did this when Steve and I were just going over some solar stuff, and so I also have a 678. Since I got the 585, I usually use that, but we were demoing the 678, so I got this with that and pretty pleased with how it came out.
Yeah, it looks great. And
yeah, I got this with my SeeStar S30 Pro. This was over about 3 nights, about 6 or so hours of time. So pretty pleased with the contrast and the detail it was able to get.
Yeah, for a 30 millimeter, that's amazing.
Yeah. Yep. And then this is also M13. Apparently I'm jumping on that bandwagon. And pulled this with my S30 Pro. And because the S30 is pretty significantly undersampled, I'm having pretty good results doing a drizzle, like a 2x drizzle when I process it, and then just cropping it down so that I get more detail on the target, and that's actually working out pretty well.
Yeah, again, for a 30 millimeter, that's amazing. Very nice job.
Yeah.
One more.
Yep, this one is my submission for the Object of the Month last month. Or I guess the month before, depending on how you how you do that. But this was with my bigger scope, my 80 millimeter. And this was about 15 hours. I think I got about 20 hours, but once I went through and got all the bad subs out, it took it down to about 15 hours, which is my first and so far longest multi-night imaging session. Very happy with how it came out, though. The chromatic aberration around some of those stars is grating, but that's mostly me.
No, again, a great picture. Ian, are you on?
Oh, yeah.
Oh.
Sorry. Yeah, so this is M51. I was just, I had a telescope out at a place called Deep Sky West in New Mexico. And over time, it got very dirty and had other issues. And I brought it home, got it cleaned up, and I've been testing in my backyard, which is essentially near downtown Rockville, Maryland. And I was just impressed that I could actually get this, given that you can practically read a book outside at night where I live. But it's just M51. What I was hoping, and this is about 12 and a half hours of data. What I was hoping to show you was how great Deep Sky West out in New Mexico is in comparison. Given that that's like Bortle 2, maybe realistically Bortle 3. So the next slide, you'll see the same thing.
Oh, wow.
But it looks the same. So I did, all the blinking between the two, and I was like, that is the most unimpressive, considering how much effort and time it takes to host a telescope remotely. So I've got to figure out what was going on there, because over time it got very dirty, but I've been very disappointed in this, considering how much easier it is to just do it in your backyard. So anyway,
Yeah.
Story to be continued there.
That is amazing from Rockville that you got that image. I mean, that's stunning. And, I mean, you're using light pollution filters, obviously, right?
No.
No?
RGB.
Oh my God. Okay. Wow.
The next one, I just started on M27. It's hard because it's been coming up at about 1 o'clock in the morning, and I'm getting tired. But so this is the first of probably another round to go on this. But I just find this one really beautiful. I've got some narrowband that isn't quite ready for processing yet that really blows this out a lot more. But this came out pretty well. Next one, I don't even remember what it is.
Drum roll.
Oh yeah.
M13.
There we go. So also the backyard. We can just move on.
All right.
Okay, so this actually goes back in my archives, but I knew people here like solar. I have a 152. This is in a single stack format. But what I ended up doing was a time lapse where I take a 10-second video every 30 seconds, sometimes every 60 seconds. For each 10-second video, I essentially do like lucky star imaging, and I get the best possible image for that 30-second segment. And I do that for 3 hours. In order to do that, you have to have like a, what do you call it? Pressurize the electronic pressurize the ailerons, so you can kind of keep tweaking those because the temperatures are changing throughout the morning. But when it works pretty well. I don't know if you can get the video working here. If you,
I just tried. I can reach it, but I'd have to go back to Zoom and tell it to look at that screen. So what I'm going to
way to get people to see it, but it is a really interesting way of viewing solar because you can kind of get a start there, but essentially you can see the, someone's going to have to help me with the terminology, but it looks like it's raining plasma down on the surface of the sun.
Yeah. What I'm going to do, because I have to send out an email to the Google group anyway with the correct time for that Venus occultation, I'll include the link there because it really is a spectacular video that you put together there. So when you guys get that email from me, be sure to check out Ian's video there because it is, again, I'm just amazed at what this group does. I mean, just fantastic. All right. So ladies and gentlemen, I think that's it for this evening. We have our planning meeting July the 6th. If you want to drop by and see how we discuss things, plan things for HAL, we'd love for you to attend. And the meeting next month is July the 9th. I forgot to check to see who our speaker is, but I'm sure it'll be another great presentation. So again, thank you everybody for coming out this evening, and please be careful heading home. Somebody probably get the lights too.
Thank you.
Thanks, and thanks for the great presentation.
I assume.
All righty. Steve, I'm going to stop the recording.
Sounds good.
Nice view of the
Hey, Steve, we got more people on solar.
Yeah. So the school.
Maybe you have to stop the recording, Steve?
Oh, I'll take a look.
School got that?
Yeah.
Oh, neat.
Since I'm on the way out, I will turn her on.